For a long time in the autonomous vehicle scene, understanding the environment a car is interacting with was and is still done using a multitude of sensors. These sensors could be thought as the eyes and ears of the autonomous car. Sensors like Lidars, radars, inertial measurement units, and cameras are all used in conjunction for the task of perception. But when we humans drive a car, we do a pretty good job of understanding where to drive and where not to drive solely using our eyes. So a very important question stems from this. Could we solely use computer vision to drive an autonomous car? Now, this is a very controversial topic in the robotics community. Even big players like Google's Waymo and Tesla disagree with each other on this. One believes that computer vision is a sole solution, while one believes that having a full sensor suite that decreases uncertainty and hence increases safety is essential for dynamic tasks such as self-driving. Although I can't answer this question for myself, I will elaborate my points and concerns through a very specific topic within the perception stack, and that is perceiving depth. Hi there, my name is Lux Jessinghani, a software team member of Monash Connected Autonomous Vehicles. And this project I'm going to talk about is a deep dive into unsupervised depth estimation.
Before we move into the bread and butter of this research project, let's talk about depth perception in self-driving cars and how it has changed over the ages. When talking about figuring out how far objects are, the first thing that comes to mind is a Lidar sensor. These are extremely accurate sensors and have a high refresh rate, so using them in an autonomous car makes perfect sense, at least in theory. These sensors are expensive, on average costing about $5,000 per sensor, and some autonomous cars use multiple Lidars at once. This induces a toll on autonomous vehicle prices at economies of scale. They also provide extremely sparse point cloud data and perform terribly in adverse weather conditions like rain and snow due to the diffraction of the laser beam. Now, even if a Lidar is chosen as a primary sensor for its accuracy, it's much safer to create a fail-safe secondary sensor to fall back on if something goes wrong. Therefore, computer vision and deep learning-based depth estimation methods are becoming more prominent. The idea is that as compute gets cheaper and smaller each year, we can just add more of it into an autonomous car. If this is the case, we can use compute-heavy systems like deep learning more accessibly, removing the need for such expensive sensors. To understand what we have to do, let's look at the problem we are trying to solve first. By looking at this image here, I can say that this car is closer than that one, which is then closer to the building over there. We know this as a fact because we built such a conception by interacting with the world using our eyes in the first 3 months as babies. Therefore, we need to create a system that inherently learns what depth is from an input image, so that we can predict depth. With traditional deep learning based approaches, supervised training with real ground truth depth is used. This means that you show a convolutional neural network tons of input images and what the output should be, and optimize the difference between these predicted images and the ground truth labels, so that you can make better depth predictions in the future. These pipelines are currently the most accurate ones out there, and are a great idea to implement in an autonomous car. But the key to having such an accurate model is large amounts of structured and labeled data. This structured and labeled data is a rarity in large-scale applications, especially in autonomous driving. Creating correctly calibrated ground truth labels is a challenge when the training data needs to be constantly generated to improve these models over time. The question that we should ponder next is, could we make our deep learning models interact with the world to explain depth as we did as babies rather than showing ground truth depth examples?
So how do we train these depth models without any ground truth labels? Is there a way to manipulate the previously mentioned supervised training pipeline in a way that could force these models to predict depth? Well, before machine learning became the norm, computer vision researchers figured out that there were geometrical certainties that connected the image plane to our 3D world. If there was a way that we could induce these geometrical certainties into our deep learning models, we could theoretically predict depth without any ground truth labels. And that is actually the case. Geometry here comes to the rescue. So to understand how such a system might work, let's build it up step by step. Let's start with something really simple and add complexity as we go along, hopefully to end up with the unsupervised depth learning architecture this research project proposes. Alright, let's begin.
As we need to predict depth, let's first start by creating a simple encoder-decoder type convolutional neural network, as we do in supervised training. This should be our depth network. Passing an image to this network, we can see that a CNN with randomly initialized weights is really good at picking up texture. Now, to force this model to predict depth, we fall back onto the geometric priors from early computer vision research. In particular, we will use a structure for motion approach, but rather than using feature matching, we would use a neural network to optimize for depth. To understand structure for motion, we would have to take a slight detour. Imagine driving on a straight road and clicking pictures as you move along. Let's look at a small time step within the overall drive. Let's say we take 3 pictures at time t-1, t, and t+1. Let's say that we also have an accurate depth map of each time step that was collected by our Lidar sensor, and an accurate ego motion of the vehicle collected by the onboard IMU. We can therefore use something called view synthesis to synthesize each image from one another. Simply put, view synthesis is a process of applying a certain transform to warp an image to create another normal view. When done in pixel coordinates, this is known as an affine transform. This is exactly what photo editing apps use to rescale, skew, or add funny warping filters to an image. A similar thing can be done in the camera coordinate system, but rather than the transform answering how much would you like to rotate an image, the transform are the actual camera poses. That is, the real movement of the camera in 3D space. Let's say we take 2 images of that red ball that's d distance away from the camera. These images were taken while moving at a certain velocity sideways. We can use this velocity information to create an accurate camera pose transformation between these 2 images. Knowing this information, let's look at a single pixel of the red ball on the first red framed image taken. This pixel can be moved from pixel coordinates, described by an x and y value, to image coordinates by multiplying this pixel's location with the inverse of the intrinsic camera matrix. This matrix contains all hidden information about the camera sensor and lens, like focal length and scale. We can then use the depth information about this image to scale this image coordinate to its corresponding camera coordinate, that is, the real location of the ball in 3D space. This is called image reconstruction. Now that we know the pose transform between the 2 cameras, we can apply that transform to the pixel in camera coordinates by a simple matrix multiplication. Doing so gives us the pixel location that ball contributes in a whole nother camera coordinate system. We can then apply the reverse of the previous mentioned steps. We multiply with the intrinsic camera matrix and descale the image coordinates to get the actual pixel locations on the next frame. This whole process is called image projection. Let me play that back again just for clarity purposes. Alright, now let's get back on track. We just learned that if we have a pose transformation and per pixel depth, we can create another image using view synthesis. If the new image created is exactly the same as the original image of the next frame, both the pose transformation and depth must be accurate. There is no 2 ways about it. So let's use the structure for motion technique to build upon our model. Rather than using a single image though, let's use 3 at different time steps. Now we need to include some sort of pose, but rather than using ground truth ego motion, as this would be considered semi-supervised, let's add another neural network that uses these 3 images to predict the pose transformation between them. The poses are predicted as a 1/6 vector of Euler angles for the 2 different images. To predict accurate depth and pose of the neural networks, we can use the same view synthesis technique explained earlier to create the target image. We first back project the depth to 3D, and use the predicted poses to transform these source points into new source views. We can then sample from these new source views, the images at time t-1 and t+1, to create images of the same target scene, the image at time t. One thing becomes very clear by looking at this pipeline. It is that if the similarity loss between the reconstructed images and the original target image is 0, the images have to be the same. Therefore, the pose must do an accurate warp, but that would only happen if the depth is accurate. So all we have to do is optimize over the similarity of the reconstructed images. And there you go, we just created a closed-loop, fully differentiable structure-from-motion-based depth estimator that can be trained with no ground truth labels at all. And here's the final result. Although we spent quite a bit of time training this model, at runtime we were able to achieve depth predictions at 10 frames per second. This is the same frame rate that had to be met according to our requirements analysis. This frame rate has been achieved because we moved all the computation from the network side to the training side. That is, we just used a simple model with less parameters, but used a lot more compute time while training.
There are quite a few intricacies I haven't touched on yet that are essential for getting such a method to work. Although these are out of the scope of this quick video, I would like to summarize these intricate requirements by stating that proper weight initialization and model constraining is essential. As this is an unsupervised approach, sometimes a model can create its own version of the problem on hand, like red cars are always further away than black ones and so on. Therefore, creating an equilibrium condition that keeps this pipeline in check is mandatory. Now that we've got all the tedious stuff out of the way, let's create an experiment that proves what we set out to do in a more general way. Usually, fancy math that looks at uncertainty induced in an image, or model uncertainty, error rate, etc. are used to check this. But let's take a more fun approach. So here's an image from the previous clip you watched. Now, to start our fun experiment, let's throw something at the deep model that it's never seen before. Let's give it something that it least expects. As you can see, the model wasn't ready for what struck. I won't judge the model too hard on this though, probably because we don't usually see life-size coronaviruses while driving. So let's test something that's a bit more realistic, like a fridge in the middle of the road. The model does a pretty good job to identify where the object is and how far it might be. Although it does hallucinate connections between objects like the fridge morphing into the tree and ground. Let's add a shadow at the bottom of this image to see what happens next. As you can see, the model does a solid job of differentiating between the ground and the object now, but still performs relatively similar everywhere else. The assumption here is that semantic meanings like change in texture and shadows are really important in depth prediction. To test this, let's place a car with shadows on an image. As expected, the model does a good job. Creating a hole in the center of this car now shows that these depth models decide on how far an object is, or the space within it, by focusing on the edges. In the future, inducing this model with semantic segmentation information might actually help it increase its performance. Now that we've talked about research, I want to share another aspect of this project. To learn more about deep learning models that are trained at industry at scale, I built an MLOps pipeline that helped with continuous integration, testing, development, and model monitoring. The idea was to be able to create an automated system that I could just set and forget. As training usually took 8 to 9 hours, using weights and biases helped me monitor my model through my smartphone, so that I could stop training my model if things go south. Another issue I faced when working remotely was that computers at our workshop would sometimes just go down. I would lose all training progress until faculty members would turn it back on. To help with this, DVC and model version control was implemented. DVC would automatically upload the weights of the model after each epoch to a Google Drive that I could pull onto another computer for further training. GitHub Actions and CML were used to train models locally in a containerized environment. This means that I could commit small hyperparameter changes in the training config file directly on GitHub. I could do this on my smartphone if I wanted, and it would start training the whole pipeline locally on the computer at the workshop that has GPUs, without me needing to log onto the computer, set the environment up, and run shell scripts. So before I end this video, I would like to thank a few people without whom this project would have not been possible. First and foremost, I would like to thank my supervisor, Dr. Michael Berg, for providing invaluable guidance, not just for this project, but also on how to think about things in general. His support extended way beyond just a unit at university, and I'm extremely grateful to have had the chance to work with him. Secondly, I would like to thank the whole of the MCAT team for their incredible team spirit. They kept me accountable and motivated throughout this project, and provided all necessary equipment, even through the arduous circumstances created due to COVID-19. Finally, my gratitude extends towards all friends and PhD students I met along the way, especially Marcus Hiller, who provided helpful tips and tricks to not only complete this project by achieving results, but to also make it through with a positive mindset. Thank you for watching.